Okay, so we're going to start our online lesson. I want to start out by looking at our schedule. So this weekend we have a lot of stuff to go over because we're going to prepare for our Tuesday test. If you pull out your worksheets and everything that I have given you, it's better, you'll make better use of your time if you have the paperwork right in front of you as opposed to just watching the video. So we're going to take out our schedule right now and look to Tuesday, October 25th, and you will see that you have a test on Chapter 4. So that means we have this weekend to prepare. We need to complete 4.5, we need to complete 4.6, and you also have worksheets to do. You're going to have to submit worksheet 4.5. I have here it's due Friday. Obviously, it's not going to be due Friday. You're going to want to move that down to Monday. Worksheet 4.5 will be due. And then the day of the test, you're going to want to have finished worksheet 4.6. Okay, so I'm just giving you a overview of where we're headed today for this video. Now what I'd like for you to do is take out your notes, and the best way to do this is to highlight as I highlight and read along with me. Mark your paper up because these notes, I think, are the best way to study for the test. You're going to want to read all of this over again. Alright, so let's get started. We are talking about the oxidation of metals by acids and salts. There are many kinds of redox. Redox is short for reduction oxidation reaction. There's many kinds of these reactions. An example is a combustion reaction where you get hydrocarbons and oxygen, and in the presence of energy, a spark, you'll get fire, and the product is water and carbon dioxide. And if you were to assign oxidation numbers, you would see that hydrogen gets a +4 charge, and carbon is a -4 charge, and oxygen is 0. And then on the product side, water, oxygen has a -2 charge, hydrogen has a +2 charge, and carbon dioxide, the oxygen, has a total contribution to charge of -4, and carbon has a +4. So if you were to draw lines, carbon, right, to on the reactant side, and you draw a line over to carbon on the product side, you can see that it went from a -4 to a +4. That is a loss of electrons, and that means carbon experienced oxidation. And the way that you remember that is an acronym, and you're going to want to write that here on the left side of your notes. It's Leo the lion says grr. Okay, this is the easiest way to remember what's going on. Leo the lion says grr. Leo is loss of electrons is oxidation. Gain of electrons is reduction. So you can see here that the carbon on the reactant side, has a -4 charge, but on the product side, the carbon now has a +4 charge. This tells me carbon has lost electrons when the reaction completes itself, and a loss of electrons means it has been oxidized. The process experienced oxidation. And then with oxygen here, it has a 0 oxidation number on the reactant side, and it becomes more negative. That means that it has gained electrons. Therefore, oxygen has been reduced. It went through reduction. Okay, now how did I figure out? If you're confused as to how I'm figuring out oxidation numbers, then I recommend that you open up to this page here in your textbook. It's page 139, and you read through the rules. Any atom in its elemental form, the oxidation number is always 0. So you should take the time to read through that. and then you understand better how I am assigning oxidation numbers. Okay, let's keep going. In this chapter, we consider the redox reactions between metals and acids or salts. Okay, so that's important to highlight because we are only going to consider oxidation with metals, acids, or salts. Here's the pattern when a metal and either an acid or a metal salt reacts. It's A plus BX yields AX plus B. For example, zinc solid, this is important that you remember that the metal's in its solid form later on for when you're doing the practice problems. And hydrobromic acid is aqueous because remember, this is aqueous chemistry. That's what chapter 4 is about. So you're going to also want to remember that you need to put the AQ after the acid. Yields zinc bromide plus hydrogen gas. This is a displacement reaction because the ion in solution is replaced through oxidation of an element. Okay, so highlight that. This is a displacement reaction. The ion that is in solution is replaced through the oxidation. Remember, oxidation means loss of electron. The oxidation of an element. Okay, so number 2. Let me move this up. Number 2. Many metals undergo displacement reactions with acids, producing salts and hydrogen gas. All right, let's take an example. Magnesium, once again, is a solid. It's a solid metal. It combines with hydrochloric acid, and that's aqueous because this is in water, yields magnesium chloride, which is also aqueous, and hydrogen gas. Okay, so we're going to look how this metal, right, it undergoes displacement, a displacement reaction, or I like to call it a single replacement reaction, with this acid, hydrochloric acid, and it produces a salt, MgCl2, magnesium chloride, and hydrogen gas. All right, so the first thing that we're going to do is assign the oxidation number. Magnesium in its elemental form, it has an oxidation number of 0. Chlorine is -1 and hydrogen is a +1. And then when you write the products, you also have to assign oxidation numbers to the products. Chlorine here is usually a -1, but since there's 2 of them, you have to write total contribution to charge is a -2, and magnesium is a +2. Because magnesium chloride, this compound has to have sum total equal to 0. So that's why magnesium's +2 and chlorine is -2. And then hydrogen gas is 0. So if you draw your lines, hydrogen was initially on the reactant side a +1 charge, but on the product side is now a 0. So as you can see, the hydrogen gained electrons and reduction took place. And magnesium has a 0 charge on the reactant side, but on the product side, magnesium now has a +2 charge. So if magnesium goes from a 0 to a +2, we know that electrons have been lost, and therefore magnesium was oxidized. Here's an important note that I have in a cloud, and you might want to highlight this. The chloride ion assigned an oxidation number remains -1. Therefore, it is a spectator ion. Very important. Notice that chlorine here is a -1. It's also a -1 on the product side because that's its oxidation number. I should have put it's important, I think, that you put the circle and the square so that you can see that. The chlorine here is a -1 and a -1. Because the chlorine oxidation charge remains the same on the reactant side and the product side, that is how you can figure out the spectator ion. You're going to want to pause this and rewind it if you have to listen to that again, because a lot of you were having trouble with finding a spectator ion, and I think here's an easy way. If you assign the oxidation number is the same on the reactant side as it is on the product side, you have found your spectator ion. I hope that makes sense. Okay. Net ionic equation is an equation where you are eliminating the spectator ion. Some of you are having trouble with molecular equations, complete ionic equations, and net ionic equations. So remember, at the net ionic equation, you have successfully located the spectator ion and you have eliminated it. Okay, so in this reaction, the net ionic equation, you can see how the chloride ion or anion has been completely eliminated. So we have magnesium, which is a solid, plus your proton or hydrogen ion. Remember, I told you that that could be called proton. Yields the magnesium ion plus hydrogen gas. Now, figure out what is being oxidized and what is being reduced in this example right here. This is on page 141 of your book. So you might want to take your book out and have your book with you every time we're doing this online. And so it's at the bottom of 141 and the top of 142. I'm sorry, it's just at the bottom of 141. Okay, so we have a molecular equation. Iron solid plus nickel nitrate, which is an aqueous solution, yields iron nitrate plus nickel, which is a solid. And you have to figure out here what is being oxidized and what is being reduced. Well, I kind of like to encourage you to do your circles and your squares for everything, only because you'll see later on as you're doing practice problems how it comes in really handy. So take a moment to do your circles and squares. And iron, we know, because of the rule on page 139, remember, this is where you find out how to assign oxidation numbers. Iron is 0. And nitrate normally has a -1 charge. How do I know that? Because of your fan. And you're going to want to keep your fan out when you're doing this. Nitrate has a 1- charge. And because there's 2 of them, that makes it a -2. And therefore, nickel has to be +2. And then now we have to figure out the charges on the product side. Nitrate is, again, -1. And there's 2 of them, so it's a -2. And iron has to be a +2. And nickel is going to be 0. Remember, don't forget the chemistry speak. The squares mean total contribution to charge. And the circles above it means the oxidation number that's being assigned. Okay, so in this case, nickel is 0 oxidation number and total contribution to charge is 0, but not in the case for nitrate. Nitrate's oxidation number is a -1, but its total contribution to charge is a -2. It's because of the subscript 2 here next to the nitrate ion. Alright, so now what you want to do next, now that you've successfully assigned oxidation numbers, you're going to want to figure out what changed. Well, right away, you're going to always start with your circle, and you're going to draw a line, this is a +2, to the change. And you're going circle to circle and not square to square. So iron went from a 0 to a +2, and when it does that, when it becomes more positive, then it has lost electrons. Remember, Leo the lion says grr. Leo, loss of electrons, is oxidation. So iron has been oxidized. And let's look at nickel. Nickel is a +2 at the circle here. And then if you draw a line over to nickel circle, you see that it went from a +2 to a 0. A +2 to a 0. That means that it has gained electrons. So a gain of electrons is reduction. Notice how nitrate, the charges stayed the same. The oxidation number for nitrate is a -1, and on the reactant and the product side, and because it stays the same, therefore you have found your spectator ion. The other thing that you want to remember, very, very important, you might want to write this down. When you're doing redox reactions, there's always, if there's an oxidation occurring, there has to be a reduction occurring as well. So you will never have two different elements both undergoing reduction. Impossible. Or two elements undergoing oxidation. That's impossible. You have to have both oxidation and reduction occurring in redox reactions. And if you don't have that, then you're doing something wrong. Okay? All right, let's keep going. Can we predict whether a certain metal will be oxidized either by an acid or a particular salt? Now remember, right now we're moving on to the activity series. So when we're doing activity series, we are thinking about, I showed you this in class already. I don't want to spend a lot of time on it because I already talked about it. The activity series is our list here with the lithium being the most reactive metal and gold being the least reactive. All right, so let's go back to our notes, but I want you to get a picture or a snapshot. When I say activity series, this is what I'm talking about. Okay. So we have the activity series here, and the question is, can we predict whether a certain metal will be oxidized either by an acid or a particular salt? From the previous equation, you would never store nickel nitrate in an iron container. And you have to answer why. Why would you, go back to what we just did, why would you not store nickel nitrate in an iron container? Iron is being oxidized, and the iron will actually fall apart. So that's why we would never put nickel nitrate in an iron container. And I'll never put food in an iron container again either because of the chemistry that happens. The redox reaction. Learned that the hard way. Alright, so you would never store nickel nitrate in an iron container. All right, when a metal is oxidized, it appears to be eaten away. So that's basically what happens if you put nickel nitrate in an iron container. The iron would eat away and would essentially look like it had a bunch of holes. And this is what happens with machine parts. Extensive oxidation of machine parts causes the machine parts to fail. Different metals vary in the ease with which they are oxidized. Zinc is oxidized by aqueous solutions of copper, but silver is not. And I already explained that by looking at the activity series. The reason why is because zinc loses electrons more readily than silver does. So let's just look at the activity series one more time. Silver is here on the activity series, and it's not as reactive as zinc. Zinc's going to lose electrons and become oxidized. Remember, loss of electrons is oxidation. And when something is being oxidized, essentially it looks like it's corroding or being eaten away. So silver being lower on the activity series is not as reactive, meaning it does not lose electrons as readily as zinc would. So, and that's why we use silver and gold for jewelry, because of the properties it has of being unreactive with many, many things. All right, so what you want to say here, because zinc is more reactive, you want to word it like zinc is easier to oxidize than silver. Zinc is easier to oxidize than silver. Anything that's high up on the activity series is going to be easier to oxidize than things lower on the activity series. So you could say calcium, plug in calcium, is easier to oxidize than platinum. Magnesium is easier to oxidize than gold. Okay, that's the way you would word that. Okay, so if you look at the activity series, which we have a few times, it's a list of metals arranged in order of decreasing ease of oxidation. Active metals, there's two different, okay, you have to know how to categorize the metals on the activity series. So this is vocabulary words, okay, so I want you to highlight that. Active metals on the activity series are metals at the top of the table. They're very easily oxidized. So lithium is an active metal. Potassium is an active metal. Barium, calcium, sodium, magnesium, aluminum, manganese, all are considered active metals. Okay, and the reason why, easily oxidized, they lose electrons. Noble metals are the other type of metals on the activity series. They are transition elements. They are found in group 8B and 1B, and they are very, very stable. They form compounds less readily, and that's why we use noble metals such as gold, platinum, mercury, well, not mercury, but silver, as jewelry or coins. And the reason why? They have a low reactivity. They're not giving up their electrons as readily as the active metals do. They're called noble metals, vocabulary word. The activity series, I'm going to say it again, activity series are categorized by two different types of metals. Active metals are at the top and noble metals being at the bottom. Okay. Number 4. Here's a rule. All right, so you might want to put, highlight this too. The rule is any metal on the list can be oxidized by the ions of the elements below it. Copper is above silver, so copper will be oxidized by the silver ions. And we went over all of this in class. Okay, so just look this over. And I also told you the mistake that I made, and I said zinc has a 1+ charge in class, and I had showed you the fan. Please correct that. Zinc has a 2+ charge, always, always, always. And silver has a 1+ charge, okay? Number 5, only metals above hydrogen in the activity series are able to react with acids to form hydrogen gas. Only metals above hydrogen in the activity series are able to react with acids to form hydrogen gas. There is one exception, but we're not worrying about that in chapter 4. But there is an exception, and we'll see that later on when Mrs. Nagel comes back. For now, only metals that are above hydrogen, let's find hydrogen, here it is. The metals above them are able to react with acids to form hydrogen gas. So nickel is the example. Is nickel above hydrogen? It is. So nickel is able to react with hydrochloric acid, and nickel displaces the hydrogen, and we get nickel chloride plus hydrogen gas. Okay, this is where I want to stop and have you work on the problems. The problems that I want to look at are the ones on worksheet 4.4. You should have assigned oxidation numbers. At this point, I don't see that you should have any issues with that. Let's just pick a couple random ones here, and then you compare your answers. Take your worksheet out, and I want you to always do your circles and your squares. Okay, don't take a shortcut here. And the reason why is because the circles are what? Circles are the assigned oxidation numbers, and the squares are total contribution to charge. This is just going to help you because remember, doing this stuff is like bookkeeping, and it helps your bookkeeping be you're going to be very precise and orderly, so you're going to have better results to getting the right answer doing it this way. All right, so oxygen in this situation is a -2 oxidation number, but because there's it's a negative, oh, she has a -1. And the total contribution to charge is a -2. And sodium is usually a +1 oxidation number. And its total contribution to charge is a +2. Okay, so the reason why oxygen, we want to read this. This is very important from page 139. The oxygen there went against the normal. The norm is oxygen is usually a -2 in both ionic and molecular compounds. The major exception is in compounds called peroxides, which contain the O2 ion, given each oxygen an oxidation number of a -1. So in this example, oxygen is a -1, and total contribution to charge is a -2. Okay. So I'm glad I randomly picked that one because that was an exception to the rule. Let's do NH4. This one, hydrogen is a +1 oxidation number, and total contribution to charge is a +4. And nitrogen is a -3. And total contribution to charge is a -3. And the reason why is because of the rule. You have to look at that. That is a actual cation with a +1 charge. And remember rule number 4, that the sum of the oxidation numbers of all atoms in a neutral compound is 0, but this is not neutral. And the sum of the oxidation numbers in a polyatomic ion equals the charge of the ion. So this has to actually add up to the charge on that cation, which is +1. All right, so make sure you have this completed, and if you have any questions, I told Mr. Nagel that you like to check the answer key to look over what you might have done wrong. So hopefully you'll be able to do that when you get to school. Okay, many of you already did this because I saw you working on it. You have to look at the problems on page 159, solve problems 49 and 50. So number 49, make sure you do all of them, but I'm going to do 49E. And it basically says, what is the charge on AS in AS, and there's 4 of them. Well, the charge on that is 0. And the reason why the oxidation charge or the oxidation number is 0 is because rule number 1, for an atom in its elemental form, the oxygen number is always 0. All right, so you're going to want to go over this. The answers are actually in the back of the book for number 49, so you can check your work at home. All right, and then I want to do one of these real quick. We're almost done. We're going to solve redox reactions and determine which atoms have oxidized and which ones have reduced. So remember, oxidation is loss of electrons, Leo the lion. Loss of electrons is oxidation, and gain of electrons, he says, gain of electrons is reduction. And hydrogen, you want to do, remember what I told you, do your circles and your squares. Hydrogen in its elemental form is a 0. Oxygen is a 0. And H2O, the oxygen in water, is a -2. And hydrogen oxidation number is a +1, but there's 2 of them, so the total contribution to charge is a +2. So you, like I said, you're always drawing the line from the circle and you're pairing it up. So you're looking at hydrogen and hydrogen. It goes from a 0 to a +1, and that means it lost electrons. And a loss of electrons, look at Leo, it means oxidation. And now we're looking at oxygen on the reactant side, and we're going to draw a line comparing it to oxygen on the product side. And we see that it goes from a 0 to a -2. It gets more negative, and when it gets more negative, that means it's gained electrons, and gain of electrons is reduction. All right, so you can do the next one by yourself, and then you're going to do the work on the back, classwork, solve problems 51 and 52, starting on page 159. So number 51, I want to do number 51B. Okay, I'm just going to do one of these with you, and you can do the rest on your own. Like I said, number 51 is already worked out in the book anyway. It's A, B, C, and D, but I want to do B. And the way that it's worded, this is on page 159 of your book. I think that these are a little bit challenging, actually. So it says here, which atom is oxidized and which is reduced in the following reactions. So we have 3F iron nitrate aqueous plus 2 aluminum solid, and that yields iron plus aluminum nitrate. Okay. So the first thing you want to do when you see this is, well, the first thing I would do is figure out what is happening here. What is this reaction? And remember, reaction. Is this a double replacement reaction? No, I already explained. A double replacement reaction is when you have a cation and an anion like as partners. So iron is a cation and it's partnered with nitrate, an anion. But over here, aluminum doesn't have a partner. So right away, I eliminate the option that this thing is a double replacement reaction. The other type of reaction I talked to you about is acid-base neutralization reaction. Mrs. Nagel just calls it acid-base reaction. Remember, that reaction is one of the reactants is going to be an acid. An acid starts with hydrogen. Okay, we don't have anything here starting with hydrogen. And a base is anything usually that ends with a hydroxide anion. And again, we have no hydroxide here. So we can eliminate the fact that this reaction is an acid-base neutralization reaction. Okay, so then what is it? This is a single replacement reaction, right? It's a redox reaction. So we're going to put our circles in our square. And we only do this, like you would never do this circle and square for double replacement reactions. Okay, you would never do this. All right. Now, let's assign our oxidation numbers. For nitrate is a -1, and then total contribution to charge is a -2. Therefore, iron is +2. Aluminum on this side is a 0. And iron on the product side is a 0. Nitrate on this side is a -1. We have 3 of them, -3. And aluminum has to be +3. All right, so iron, let's draw our lines from +2, and it's always from the circle to 0. Therefore, this thing went from a +2 to a 0. It's gained electrons. That means reduction. And let's see what happened with the nitrate. Nitrate is a -1 oxidation number, and if you go over here, it's a -1 on the product side, and when the oxidation numbers remain the same, we have found our spectator ion. And then aluminum on the reactant side is a 0, and on the product side it is a +3. It has lost electrons, and a loss of electrons is oxidation. So basically that's how you do this. Not so bad. And this, actually, I said this one was challenging. This isn't the problem that's challenging. It's the next one. We already did this. Predict redox reactions based on the activity series. And if you want to take one, let's just look at number 9 for those of you who still feel a little confused. Redox reactions, zinc here with silver nitrate. What you're asking yourself, does zinc have the ability to displace silver and bond with the nitrate anion? And the way that you predict that is you look at the activity series and you see that zinc is above, here's zinc, and zinc is above silver. And because zinc is above, by rule, zinc is more reactive and it will displace silver. So now we're going to get zinc nitrate. And zinc has a has a 2 charge on it. And the reason why I know zinc, it's Zn, zinc nitrate, and the subscript 2 is, remember, you need this fan. If you need me to scan the fan because you lost it, you really need it. And I'll be more than happy to scan it and send it to you, but you need to know that zinc always carries a 2+ charge. And that's why the compound is written like this, zinc nitrate with a subscript 2. Zinc has a 2+ charge. And that's going to be aqueous, and silver, solid. Okay, so the answer is yes. This reaction will take place. Remember, there's certain examples where no, it will not. Let's look at number 7. No, the answer will be no here, because you're predicting whether the following reactions can occur. Copper, can this reaction produce copper chloride? Well, let's look at where copper falls in relation to sodium. Copper is, well, here's sodium. It's pretty high up. And copper is way down here. So copper is not reactive enough. It does not have the ability, because it's lower. Copper is lower than sodium. Therefore, no, the reaction will not take place. All right, this is the one that I thought was a little bit challenging. Page 160, number 53 and 56. So number 53, there are A, B, C, and D, and the way that what it asks you to do is write balanced molecular and net ionic equations for the following reactions. So these are difficult because they not only, you have to know how to balance the reaction, or balance the equation. So I want to do B, chromium with hydrobromic acid. So this is B, and it's number 53. And chromium is going to be a solid because it's a metal by itself. And then we have hydrobromic acid. That's an aqueous solution. And that yields, well, first off, you have to look on the activity series to see if chromium has the ability, can chromium displace hydrogen? That's what you need to know. So if you look over here, hydrogen's right here, and chromium's way up here. The other thing you need to remember about chromium, as soon as you hear that, you should be thinking to yourself, chromium is an ion that always carries a 3+ charge because of what I showed you with the fan. And if you don't have that known by heart, then you need to do the fan all over again. Start over, and you're going to want to write this all out, and then you're going to want to turn it over and, work it the way I showed you. Keep on turning the paper over so that you can commit this to memory. Okay. So the other thing you want to know is, okay, yes, chromium can displace hydrogen, and the other thing is chromium has a 3+ charge. And that's going to produce chromium bromide plus, and that's chromium bromide with a subscript 3 because of the charge on chromium, plus hydrogen gas, and this is aqueous. All right, so what it wants you to do is write out the balanced molecular equation. So if you were to balance this thing, it did take me a little bit of time. The trick is that you remember chromium has a 3+ charge. That's one thing you have to remember. So when you work it all out, it ends up being 2, 6, 2, 3. But I recommend not taking my word for it and just working it out yourself to try to get that thing balanced. And then the next thing, so this will be your balanced molecular equation. And then the next thing they want to know is, what is your net ionic? And remember, net ionic is minus the spectator ion. So if you give these things assign oxidation numbers, chromium is 0 here, and bromine is -1, hydrogen is +1, and bromine is -1, -3, and that makes chromium +3, and hydrogen gas is a 0. All right, so let's just do this real quick. Chromium, as you can see, goes from a 0 to a +3 charge. It loses electrons. Loss of electrons is oxidation. Hydrogen goes from a +1 charge to a 0 charge, and that means that it has gained electrons. That's reduction. But let's look at bromine. Bromine stays the same at a -1 charge. That means that is your spectator ion. So when you write your net ionic equation, it is going to be it has to be balanced. So it's going to be 2 chromium, and that's a solid, plus 6 hydrogen ions, yields, and that's aqueous, yes, aqueous, and then that yields 2 chromium cations with a 3+ charge, and that's aqueous, plus 3 hydrogen gas. So this is your net ionic equation, minus the spectator ion, which is bromine. Okay, so that's about all I want to do for now. Make sure that I just gave you enough information that you're able to totally complete worksheet 4.4. It's due when you go to school on Monday, and tomorrow we are going to go over the notes for worksheet 4.5. Talk to you soon.